All right, so we are very happy to have Professor Dakshita Khurana from University of Illinois at Urbana-Champaign. She works in the field of cryptography, and she has got a very exciting work on designing a new cryptographic primitive, which she will tell us about. Over to you, Dakshita.
Thanks everyone for having me here. I am going to talk about building SNARGs, which are succinct non-interactive arguments. So these are important tools in the study of verifiable outsourcing of computation. So building SNARGs and proving the hardness of the complexity class PPAD based on a standard cryptographic assumption, which is the learning with errors assumption. And this is based on joint work with Ruta Javale, who's my student at UIUC, Yael Kalai, who is at MSR and MIT, and Rachel Zhang, who's a student at MIT. And I want to specially acknowledge Ruta Javale, who's most of these slides have been borrowed from her. So in this talk, we're going to concern ourselves with certain specific types of interactive proof systems. First, let's recall the concept of an interactive proof. Sorry, before I go on, I just want to say that if you have any questions at any point of time, please feel free to interrupt me and ask. Yeah, so interactive proofs are basically a protocol between a prover that's relatively powerful and a verifier that's relatively weak. The prover and the verifier engage in multiple rounds of interaction in which the prover aims to prove the validity of some statement of its choosing. We typically have the following requirements. The first is that if the statement that the prover is trying to prove is true, then an honest prover should always be able to convince the verifier to accept the proof. And if the statement is false, then no dishonest prover should be able to convince the verifier to accept the false statement, except with negligible probability. That took a while to show up. Now, interactive proofs with unbounded provers and polynomially bounded verifiers are well known to be extremely powerful. In fact, they are known to be equivalent to in complexity to the complexity class P space. And protocols that achieve soundness, which is the second condition, which means that a cheating prover that's unbounded cannot fool a verifier. So protocols that achieve this property in settings where the prover is allowed to run in unbounded time, and so there's no bound on the running time of the prover. In this setting, the interactive protocol is called a proof. And beyond their complexity theoretic power, interactive proofs have many important applications in cryptography. One of the most important of these applications is to enable fast and cheap verification of expensive computations. So we will discuss this application and its use in cryptography more concretely in some time. For now, let me add a few specifics to this definition of proof systems. In this talk, we are going to focus on interactive proofs that, in addition to the correctness and the soundness property that we just defined, will also satisfy an additional property that's called the public coin property. So this just means that all the verifier's messages, which we will call challenges, are sampled uniformly at random. So this is what is called a public coin interactive proof system. So now in most modern applications of interactive proofs, which include delegating computation, where a weak client wants to make sure that a powerful server performs some computation correctly in such a way that it's very cheap to verify that computation was correctly done. And another application is blockchain, and cryptocurrency transactions, where we want to have succinct, extremely efficiently verifiable proofs that transactions were being computed correctly. And so, in fact, these types of proofs and their cryptographic variants are finding actual applications in actual cryptocurrencies that people are using today. And in these applications, it becomes crucial to not have multiple rounds of interaction in this game between the prover and the verifier. What we would like to have, and what is practically very useful to have, is a non-interactive protocol where we assume the existence of a trustworthy source of randomness that generates what is called a common reference string. And we ask if it's possible for the prover to convince the verifier by sending a single message to the verifier. Now, again, if the statement is true, the verifier should be convinced. If the statement is false, the verifier should not be convinced, except with a probability that is negligible in an asymptotic security parameter. And in this setting, we will need to consider a prover that is computationally bounded, as opposed to the previous case where we assumed that the prover could run in unbounded time and it would still not be able to cheat. Here, on the other hand, it becomes important because of cryptographic lower bounds to put a bound on the running time of the prover. And by putting a bound, I mean that we just assume that the prover is a probabilistic polynomial time machine, as opposed to a machine that can run in unbounded time. And we will make cryptographic assumptions, which will basically be of the form so-and-so is hard to solve for probabilistic time machines. And under this type of an assumption, we will aim to build such non-interactive arguments. Now, a very natural, yes.
Sorry, quick question. So here in the second question, in this setting, the prover has some additional information that enables the prover to verify, to sort of convince the verifier and so on?
Yes, that is correct. So the prover typically has some additional information and is trying to convince the verifier. Another way to think about this is that the prover runs in a large amount of polynomial time, but still polynomial, and the verifier runs in a very small amount of polynomial time. So if you think of security parameter lambda, the prover's runtime is polynomial in lambda, and the verifier's runtime can be as low as polylogarithmic in lambda. So yeah. And so now a very natural question that comes up in this setting is whether it is possible to convert interactive proofs, which had that interactive many round structure that we saw before, to non-interactive arguments, where again, there's a single common reference string and the prover sends a single message to the verifier. And in fact, luckily, there does exist such a general purpose transformation in the literature. This is called the Fiat-Shamir transform. So this is a transform designed exactly for this setting, which says you can take an interactive proof and using a specific object that I will talk about in a little bit, it gives a way to convert this proof into a non-interactive argument. Now, the way that this heuristic works is that it, for any interactive proof, it gives a way for the prover to non-interactively and on its own generate all these protocol messages, given access to some set of hash keys. So in other words, the common reference string will just be a bunch of hash keys for an appropriately chosen hash function. And now instead of the prover and the verifier interacting many times, what the prover is going to do is it'll compute the first message of the interactive proof. And then for the verifier's message, it's just going to hash this first message using the first hash key and some appropriately chosen hash function. And this is going to result in some value R1. And the prover is just going to pretend that this is what the verifier's challenge was going to be. Okay, so basically the prover is non-interactively emulating the function of the verifier by hashing its messages. Next, given R1, the prover is going to compute M2. Again, there is a one-to-one correspondence between the protocol on the left and the protocol on the right. And the only difference is that instead of the verifier sending values R1, R2, R3, and so forth, the prover is just generating them on his own by applying this hash function to its messages. So basically, at any point in time, the prover hashes the transcript that it has created so far, and this gives it the next message of the verifier, the next simulated message of the verifier, and it goes on in this way. And once it has collected an entire simulated transcript, it simply sends the simulated transcript altogether to the verifier. Right? So really the only difference between the left and the right protocol is that instead of the verifier generating R1, R2, and so forth, in the right, R1 is generated by the prover himself by hashing the first message. Similarly, R2 is generated by the prover by hashing M1, R1, and M2, which is the transcript so far, and this goes on. Okay. hopefully this is clear. Now, this is a really useful heuristic, and it's used all the time in practice. In practice, the hash function h is sometimes instantiated as the SHA hash function, sometimes as the as AES. But all of these hash functions are basically assumed for the purposes of the proof of security of this protocol. All of these hash functions are assumed to imitate what is called a random oracle. So to prove soundness of this transform, what actually seems to be needed is the following. So if you look at the protocol on the left, let's look at the very first round of messages. The prover sends M1 on the left, and the verifier responds with R1. The soundness of this interactive protocol is actually derived from the fact that the dishonest prover is committed to M1 before it knows what the verifier's challenge R1 is going to be. And the idea in most of these interactive proofs is to catch a cheating prover. If it commits to some M1 and it's trying to cheat, then with high likelihood over the randomness of the verifier's next challenge, the prover is going to get caught. So that's the very high level idea behind why these interactive proofs are actually sound. Now, sorry, another way to think about...
Can I?
Yes. Yes.
So maybe you said this. So are you assuming that your original interactive proof had this sort of standard form where verifier only sends random strings to
yes,
prover?
Yes. Yes, yes. So like I mentioned towards the beginning of the talk, we are assuming we are only going to work with public coin interactive proofs. And so that means that all the verifier's challenges are random. Yeah, I'm sorry, I should have reminded everyone of that. So thanks for asking.
Thank you.
Yeah, so we are assuming that all the verifier's challenges are uniformly random values. And that's why it's possible for the prover to emulate them all by applying a hash function. Now, yeah, so intuitively, we said that the soundness of the interactive proof follows because the prover is committed to M1 before it sees R1, and then committed to M2 before it sees R2, and so forth. So now if we try to analyze the soundness of the non-interactive protocol on the right, if we use a hash function, which makes it so that R1 is uncorrelated with M1, and then R2 is uncorrelated with M2, it seems like such a hash function should lead to a sound protocol. In other words, in a non-interactive setting, we want to make sure that no matter what the prover hashes, it should not be able to compute and generate an M1 and R1 that are correlated in such a way that the earlier M1 is somehow a function of the later R1. So this intuition will become more clearer as we go down, as we proceed into the talk. But let me just say here that in other words, we want to choose a hash function carefully in this setting so as to make sure that its inputs, which is like the M values or the transcript so far, and its outputs, which is these R values, are fairly uncorrelated. And actually, it turns out that the exact property of being uncorrelated that we would need can be formalized or can be captured into what is called correlation-intractability. So these types of hash functions that suffice for the soundness of the Fiat-Shamir transform that I just told you about were first introduced in the work of Canetti, Goldreich, and Halevi, and these are called correlation-intractable hash functions. So a hash function is said to be correlation-intractable with respect to a sparse function f if it's hard to find inputs x such that hash of k comma x equals f of x. So basically, it should be hard to find an x such that hashing x would lead to f applied to x. And this is the correlation intractability property that is necessary for the previous transform to go through. And again, we're going to see why that is the case very soon. So hopefully this will, the reason for this will become clear to you within the next 20 minutes. But I do want to make sure that the property, that everyone understands what the property is.
What does sparse mean here?
Right, so that's not properly quantified, but we want to say that for any function f, if it's hard to find So, okay, so sparse basically means that the function is, okay, let me just do this. Right, so a sparse function basically means that if you were, okay, I should quantify this properly, but if the hash function was replaced by a random function, then this probability would be negligible. So if instead of using the hash function that we are using, if this was just a truly random function on the left, then the probability that a truly random function equals f of x should be negligible. So that's what we mean by a sparse function. And I'm sorry, this is not evident from this slide, but it will become evident soon. Again, like the important correlation intractability with respect to a function f property is just that, I mean, this can be defined with respect to arbitrary functions. It's just hard to construct with respect to arbitrary functions. But the definition is just that it should be hard to find an x such that hashing x leads to output f of x.
I also had a question. So this, what is PPT and what does it stand for here?
Oh, right. Yes. So PPT stands for probabilistic polynomial time machines, okay. Which is basically a cryptographic way of saying that we don't get information theoretic security, but only a computational version of security against adversaries that can run in polynomially bounded time and can toss coins.
And so this A gets a unary input of some length and then followed by the key to the hash function.
Correct. Yes. So A gets a unary input of length lambda. That's just another way of saying that A can run in time that's polynomial in lambda. And it, in addition, gets the hash function's key. And given this key, it has to find an x such that hash of x is equal to f of x. And the probability that it successfully finds such an x, we would like it to be a negligibly small value. Thank you. Okay.
So here you're using the fact that sort of the hash function is just a little more difficult than the time that a little more difficult with respect to the running time that A is allowed?
Not really. The A is allowed any unbounded polynomial amount.
No, it has to be equal to fine. It's sort of an inverse problem. Yeah.
Right. Yeah. Sure. So we are just using the fact that the hash has some cryptographic property that prevents an adversary from efficiently finding such an x. So again, this is not, if the adversary was allowed to run in more than polynomial time, then it would definitely, like, then we wouldn't be able to talk about any type of security at all. Okay, so I think these things, I'm hoping that these things will become a little clearer once we actually talk about why this is useful in the protocol, like the definition should become more evident. But let me just take a quick aside and talk very, very quickly about this random function that I just mentioned. So there's something called the random oracle model, which basically gives all entities, including the prover and the verifier, access to a truly random function. So what this means is that in this random oracle model, instead of using some keyed hash function, what we can do is in the Fiat-Shamir transform, we can build a non-interactive argument by applying the random oracle to the transcript so far. So as opposed to computing hash of M1, which is what we were doing before, we've replaced hash of M1 with this truly random function applied to message M1. And now if you're applying a truly random function, clearly the outputs are uniformly random and there's no correlation between inputs and outputs. And so a truly random function is indeed a correlation-intractable hash function. And so what is actually done in practice is that the hash function SHA, which is not truly random, is still assumed to be sufficiently indistinguishable from truly random. And it is just assumed that this transform, when using SHA instead of an actual random function, is secure. So this is a very important model that's used very often in practice. It was introduced in a work by Belleret and Rogovey, and it was also proven to be sufficient to instantiate the Fiat-Shamir transform. Again, the idea is that a truly random function does enable the transform to go through. The problem is that in reality, such truly random functions that are efficiently describable cannot exist. That's because a truly random function demands that there is an efficiently described function that embeds an exponential amount of entropy. So no actual hash function, not SHA, not AES, no actual hash function can be actually used to construct a random oracle. And so this is all heuristic. And our goal in today's talk is going to be to remove the need for these heuristics and remove the need for the random oracle and actually construct such hash functions that enable the Fiat-Shamir transform to go through from nice cryptographic assumptions that don't require us, for example, to assume impossible things. And towards this end, let me just say that there's been an exciting line of work achieving these hash functions that are needed for the Fiat-Shamir transform under a sequence of assumptions that have been relatively strong. In particular, there's been a beautiful work that came out last year of Canetti et al. And of Pikert and Shehan that constructed such hash functions under the standard cryptographic assumption of learning with errors. And this was for a special class of functions, namely those that are efficiently computable. And using their construction of correlation-intractable hash functions, these works were able to obtain non-interactive zero-knowledge arguments for the complexity class NP. Since this talk is not about zero knowledge, I'm not going to define what this is. I'm just going to say that this was an important result and solved an important open problem in the field. But despite all these impressive results, this restriction to the class of functions, namely those that are efficiently computable, bottlenecked the applicability of these prior works. And in particular, instantiating the Fiat-Shamir transform for larger and more general classes of interactive proofs implies the existence of two very interesting results. The first is a succinct non-interactive argument, which I will formally define in the next slide. And the second is the hardness of the complexity class PPAD, which is polynomial parity arguments on directed graphs. And if you don't know, again, what these words mean and how they're defined, don't worry, we'll define them in a few slides, or I'll tell you more about them in a few slides. The focus of this work is on constructing these objects, so SNARGs as well as PPAD hardness, and achieving these results under standard cryptographic hardness assumptions. And specifically, we will build them under the sub-exponential hardness of the standard LWE, or the learning with errors assumption. Now, unfortunately, in this talk, what we do is we use other cryptographic primitives that are based on LWE as a black box. And so I'm not going to go into the definition of learning with errors because that is not going to be as important to understand how our constructions work. It's mainly prior work that uses LWE to build a few things, and we are able to use those things in a black box way. But if you're curious, let me just say one line about the LWE assumption here. So this is a cryptographic assumption that's been studied for a few decades now. And the overall idea is that it is hard to solve systems of noisy linear equations. So if you take a bunch of linear equations and you add a little bit of noise to them in such a way that the equations are still overdetermined, that means there exists a single solution. The LWE assumption says that this solution is hard for polynomial time machines to actually find. And so that's all I'm going to say about this assumption. And don't worry, you don't need to know more about it in order to understand this talk. Now let's take a closer look at the first application. So our first application is a succinct non-interactive argument, which, similar to the definition of non-interactive arguments before, there's going to be some shared information, the common reference string at the start of the protocol, and the prover will have to convince the verifier by sending them a single message that a given statement is true. And again, as we, something went wrong. I'm sorry about that. But yeah, as we said before, these non-interactive arguments should be correct, which means if the statement is true and the prover behaved properly, then the verifier should accept the proof. They should be sound, which means if the statement is false, then no matter what the prover tries to do, as long as the prover is polynomially bounded, so it's a probabilistic polynomial time machine, the verifier should not be convinced and should reject the proof. And finally, the succinctness property says that the proof should be short and easy to verify. So for the purpose of this talk, what do we mean by short and easy to verify? In this setting, we'll consider a circuit of depth d such that if x is in L, then the circuit applied to input x outputs 1. And we will say that a proof is succinct if the size of the CRS and the size of the proof grow linearly with the depth of the verification circuit and polynomially with the security parameter. The prover's runtime, on the other hand, can grow polynomially with the size of the circuit and the security parameter. And the verifier's runtime grows with the size of input and then an additive factor of the depth times polynomial in lambda. So another way to think about this is for security parameter that looks like k. So imagine a different security parameter k such that poly in lambda is actually polylog in k. And so replace these poly and lambda terms with actually polylogarithmic terms. So that roughly means that the size of the CRS and the size of the proof is polylogarithmic. The verifier runtime is also polylogarithmic. And on the other hand, the prover runtime only grows with the size of the circuit that the prover is trying to prove. So again, importantly, I want to emphasize that the verifier's runtime and the size of the proof are independent of the size of the circuit that establishes the validity of the statement. Okay, so that means the verifier is able to verify much more efficiently than running this decision circuit that decides whether X is in the language or not. Sorry, I've said that a bunch of different ways now. I hope that was clear, but I can, yeah, please let me know if there's questions. Okay. So there's been an exciting line of work which achieves SNARGs under a variety of relatively strong assumptions. In particular, starting with the important works of Killian and McCarley, who first studied SNARGs and showed proofs assuming random oracles, which were these truly random functions I was talking about. And then there's been a sequence of works that assumes what is an important or an up-and-coming cryptographic primitive called indistinguishability obfuscation. Then there were more recent works that assumed optimal security of fully homomorphic encryption. So basically all of these use relatively heavier tools and stronger assumptions to obtain succinct non-interactive arguments for the complexity class P. More recently, there was a work by Kalai et al. That introduced a new pairing-based falsifiable assumption under which they were able to achieve SNARGs for the class P as well. This work, on the other hand, that I'm going to talk to you about is able to achieve SNARGs for languages that are decidable by bounded depth circuits. So like in the previous slide, we said that if the depth of the circuit is D, then the size of the proof and the verification runtime is going to grow with D. And under this relative efficiency constraint, we will achieve SNARGs under the better sub-exponential LWE assumption. That's better than these assumptions that we just talked about before. And since sub-exponential LWE is widely believed to be secure against quantum adversaries, we actually also are the first construction to achieve post-quantum security. So again, why this is true and why the LWE assumption is believed to be post-quantum secure is outside the scope of this talk. But the next thing I want to say is that it turns out that the same techniques that we use to obtain SNARGs for bounded depth circuits also have implications to the hardness of computing the Nash equilibrium of two-player zero-sum games. And in particular, there's a very well-known complexity class called PPAD that contains within it the problem of computing a Nash equilibrium. So the full form of PPAD is polynomial parity arguments on directed graphs. And this is the class of all search problems reducible to what is called the end of the line problem. Again, for the purposes of this talk, definitions of the end of the line problem and of PPAD are not going to be very important. And we won't discuss the definition of the problem, but I'll just note that this class includes the problem of finding a Nash equilibrium in a non-cooperative game. And as I'm sure you're aware, finding a Nash equilibrium has important implications to the field of game theory and economics because of being such a central problem. And now, due to the importance of this problem, it's important to understand whether it is important to understand whether this problem is easy or hard to solve. And so to that end, there's been a line of exciting works that achieve PPAD hardness under a variety of relatively strong cryptographic assumptions again. So in particular, assuming indistinguishability obfuscation, and one-way permutations, functional encryption in one-way functions, under new pairing-based assumptions, under specific exponential time assumptions relating to LWE. There's been a line of work basically investigating this problem. The most relevant to our work is a recent work of Choudhuri et al., who showed that assuming soundness of the Fiat-Shamir transform that we just looked at, applied to a very specific interactive protocol, plus some other assumptions, actually can be, so under the strong soundness of the Fiat-Shamir transform applied to a specific interactive protocol, together with some other assumptions, one can show PPAD hardness. And by strong soundness, I just mean that they need a specific type of soundness that's more than the soundness property I described before. Again, for the purposes of this talk, this is not going to be very important, so I'm not going to get into the details of this. The main takeaway is that the Fiat-Shamir transform, which compresses interactive proofs to non-interactive arguments, was shown to have a direct implication to the hardness of the complexity class PPAD in this work. And this connection is something that we are also going to exploit in order to get PPAD hardness from sub-exponential LWE. Okay, so this work, on the other hand, assumes sub-exponential LWE. And like I said, prior work assumed much stronger assumptions and achieves PPAD hardness from a standard cryptographic assumption that's been studied for many decades. And moreover, again, since this assumption is believed to be quantum secure, this actually also establishes the quantum hardness of the complexity class PPAD under sub-exponential, basically the sub-exponential average case quantum hardness of the complexity class PPAD, assuming sub-exponential quantum hardness of LWE, which is widely believed by many to hold. Okay. So now, unfortunately, I don't have the time to show you why the following is true. So at this point, I will ask you to take a leap of faith with me and believe that the technical heart of both of these results, which is succinct non-interactive arguments, as well as the hardness of the complexity class PPAD, is actually what is called the sum-check protocol. So this is a very famous protocol that was introduced in the work of Lund Fortnow, Lund et al. And Shamir, and was used in the famous proof of IP equals P space. So I'll get to this protocol in a second, but the technical heart of both of these results is a proof of soundness of the Fiat-Shamir transformed applied to this sum-check protocol. So what I mean is that the goal from now on is going to be to take this interactive sum-check protocol and find a way to apply the Fiat-Shamir transform to it under the sub-exponential hardness of LWE, which means we will construct an appropriate hash function that allows the prover to hash all the messages of the sum-check protocol and get a non-interactive sum-check argument as opposed to an interactive sum-check proof. And once we're able to do this under sub-exponential LWE, that's going to suffice to get both SNARGs and PPAD hardness results. So now let me say a little bit more about this, famous sum-check protocol. So in this protocol, the prover and the verifier operate over a field. And the prover attempts to prove to the verifier that for a polynomial P over this field, evaluating P at all possible assignments of variables x1, x2 up until xn on on all possible assignments of these values x1 to xn in 0, 1 to the n, and summing the results up equals a field element A. So what I mean is evaluate the polynomial on all zeros plus the polynomial evaluated on x1 to xn being all, xn minus 1 being all zeros, and then the last one being 1, plus the polynomial evaluated on 0, 0, 0, 0, 1, 0, and so forth. So take all possible evaluations of the polynomial for all possible values that x1 to xn can take in 0, 1 to the n, and then add up all these evaluations. And this is over a field. And the goal is to prove that this polynomial evaluated on all these different points and summed up equals a specific field element A. Okay, so at very first glance, one will see that since this is a multivariate polynomial and it's being summed up over 2 to the n different possibilities of assignments to x1 to xn, this is therefore inefficient to compute. And so the verifier does not want to do the inefficient work of checking that this polynomial evaluated on all these elements equals A. And therefore, instead, we will design a protocol where the verifier can happily run in polynomial time, whereas it's the prover that's running in exponential time. Again, in actual crypto applications, all these parameters are scaled down. But for now, we're back to a world where the prover is exponential and the verifier runs in polynomial time. So the prover, in order to convince the verifier, the prover is going to send univariate polynomials at every step that are basically partial sums of the original polynomial P. And the verifier is going to perform a bunch of checks on these univariate polynomials. So in particular, some of you may have come across this protocol before, but let me remind you what the protocol looks like anyway. So this starts by having the prover send the univariate polynomial P1 to the verifier, where P1 is defined as the partial sum of the polynomial P over all possible assignments to x2 to xn. That means we leave the variable x1 free, and then we sum up over all possibilities of x2 to xn. As a result, we get a polynomial P1 in x1 and send that polynomial over to the verifier. Okay. So now at this point, the verifier checks that the sum of the prover's first message over all possible assignments to x1, which is basically both possible assignments to x1, actually sums up to A. If this check passes, then the verifier forwards, and this is important, the verifier forwards a randomly sampled value from the field to the prover. So the verifier is going to sample R1 at random in the field and send it on to the prover. Now the idea is that using P1 and R1, the prover has to come up with a smaller polynomial for the verifier to verify. And what do I mean by smaller? Well, the prover is just going to set the value of x1 to be R1 from now on. And so basically x1 is going to be fixed to be R1 for the remainder of the protocol. And the prover's next message is going to be the polynomial P2. P2 is the partial sum of the polynomial P with fixed value R1, x2 being the free variable, and x3 to xn summed over all possible values in 0, 1 to the n. Right? So P2 is basically set the first coordinate to R1, leave the second coordinate free, sum up over all possibilities x3 to xn, send the result to the verifier. Now, this is again a univariate polynomial in x2. And so what the verifier does on his end is a simple check, which is the verifier makes sure that P2 evaluated on both possible values of x2 and summed up is actually equal to P1 evaluated on R1. Because if the prover was honest, that's what this check should have passed based on how the prover constructed the polynomial. Okay, so basically at every step, we are fixing one coordinate, summing up over all the remaining coordinates and leaving one specific coordinate free. So in the next step, the verifier sends a randomly sampled field element R2 to the prover, and the prover can use this to, over many steps, to eventually, so okay, let me just say that when the verifier sends R2, the prover will come up with P3. P3 is nothing but P with R1 and R2 fixed, X3 as its free coordinate, and X4 to Xn summed up over all values in 0, 1 to the n. So this pattern goes on until the prover in the last round comes up with polynomial Pn, which basically has R1 to Rn minus 1 fixed in this way, and the very last variable free. And now at the end of this protocol, on receiving Pn, the verifier is going to check if Pn evaluated on Xn and summed up over both possible values of Xn and 0, 1 is actually equal to the previous polynomial, which was Pn minus 1, evaluated on the verifier's previous challenge, which was Rn minus 1. Okay. Now we just described the protocol. Why does this work? Well, it turns out that, that another way to think about what's going on in this protocol is to look at each round as the prover making some claim on the polynomial P. So the initial claim is that the original statement is true, which is that the polynomial evaluated on x1 to xn equals a. Now the verifier has no way of efficiently checking this. So the next claim is that when we fix the value of x1 to be R1, then the original polynomial summed over x2 to xn is actually equal to the first polynomial summed is equal to the first polynomial evaluated on R1. I'm sorry, I skipped P1 here, but if you recall, P1 is actually the first polynomial that the prover sent to the verifier. And so in this way, we can think of this as the prover basically sending a bunch of claims to the verifier performing some local checks on her end, and at the very last, the verifier checks the very final claim by ensuring that, again, going back here, by ensuring that P evaluated on R1 to Rn, which is what Pn is, which is what the claimed Pn is, P evaluated on R1 to Rn, which the verifier can evaluate on her own, equals Pn evaluated on Rn, where Pn is the last polynomial that the prover sent to the verifier. So the subject protocol can be viewed as a way of chaining the verifiability of these claims until this very last claim, which is directly checked by the verifier at the end of the protocol. So again, this last claim is simply that the original polynomial evaluated on R1 up until Rn equals the last polynomial that the prover sent evaluated on Rn. And this is something that the verifier can check very efficiently on her own. Now, looking ahead a few slides, this perspective will help us understand how to achieve a non-interactive argument by ruling out the possibility of cheating somewhere along this chain. Now, in order to understand this better, let us consider a setting where the original statement was false. So let's say the prover is trying to trick the verifier into believing that some polynomial P star evaluated on all possibilities of x1 to xn and summed up is actually equal to a star when, so that's the prover is trying to prove that P star applied evaluated on x1 to xn and summed up equals a star, but it actually does not equal a star. So what the prover does is it sends polynomial P1 star chosen arbitrarily, and the only thing the verifier checks is if P1 star evaluated on x1 and summed up equals a star. And then if this check passes, the verifier sends some R1 to the prover. Then the prover sends some other polynomial that it comes up with somehow arbitrarily, and then the verifier again does a check and sends a second challenge to the prover. Now, through this chain, let's look at the claims that the dishonest prover is making. And in fact, if a verifier is tricked into accepting this proof and the original statement was false, we know that if we interpret this as a bunch of claims, the very last claim is being checked by the verifier herself. So this last claim must necessarily be true. And we know that the very first claim, which is that the polynomials evaluated everywhere and summed up equals a star, if the very first claim is false and the last claim is true, then that means that there must be a step in this entire sequence of claims, some point I, at which the prover switched from proving a false claim to actually proving a true claim. So again, if the very first claim is false, and we think of these as just a bunch of claims that the prover proves to the verifier one after the other, there's some point in this chained sequence of claims where the prover switches from proving something that's false to proving something that's true. And so zooming in on this point, this means that that for some I in n, the I minus 1th claim was false, but the ith claim suddenly became true. Then just by this second equation here, this can only happen if Ri is a root of the following polynomial. The polynomial is simply pi star minus this left polynomial with Ri left as a free variable. So I'm saying something very trivial here. I'm just saying that look at the second equation. If the second equation is indeed true, that means this claim is true, then Ri must be a root of the polynomial that's written below. Okay, that's just by definition. And so now this is exactly what we want to avoid. Going back in the sum check protocol, what we actually want is that if the prover started with a false claim at the top, then it should end up with a false claim at the bottom. And since the verifier is checking this very last claim, a verifier that sees a false claim at the bottom is just going to reject the proof. So that's what we want, right? All right, so going back here, what we want to avoid is the verifier challenge ending up being a root of this specific polynomial. Because if it is a root of this polynomial, then the prover is happy, the prover can switch from a false to a true claim and trick the verifier. So to prevent this, I'm just repeating this once again, just for clarity. So to prevent this from happening, we want to make sure that the verifier's challenge is not a root of this polynomial. So let's summarize what we've learned from looking at this protocol. We've learned that the interactive prover in the sum check protocol, which basically proceeds as a sequence of claims and then challenges from the verifier, can only cheat if the verifier challenge is the root of the specific polynomial that we had listed on the previous slide. And now recall that in the interactive protocol, the verifier is sampling these challenges uniformly at random. And therefore, one can say that the probability that such a randomly sampled challenge is a root of a specific polynomial and is going to be small because the polynomial that we are interested in has only a very few roots. And so this follows from the Schwartz-Zippel lemma. But recall that in our non-interactive protocol, challenges are computed by the dishonest prover as the hash of the current transcript. So our goal is going to be to prevent the hash function that we look at from generating these bad challenges as its output. Okay, so that going back once again, here we want to prevent the verifier challenge Ri from being a root of this polynomial. And we know that this polynomial has only a very few roots. So this is what I meant by sparsity before when I was talking about avoiding a certain set of sparse bad values. And so in the non-interactive, sorry, was there a question? Okay, sorry. In the non-interactive setting, what we want is for the values Ri, which are the verifier challenges, that are being computed by the prover by hashing their transcript so far. We want these verifier challenges to not be roots of this polynomial, because that's what is going to prevent the prover from cheating. Okay, and so we will call these roots of this polynomial as bad challenges, because that's what we want to avoid. And because the only way for the prover to cheat is if the verifier's ith message, Ri, was equal to this bad challenge or a root of this polynomial. Okay, so we will call this challenge that allows the prover to cheat more generally a bad challenge. And at this point, this sounds suspiciously similar to the definition of correlation intractability for hash functions that we had looked at before. In particular, a correlation intractable hash function makes it hard to find an x such that hash of x equals f of x. And if we think of f as being the function that is equal to the root of the specific polynomial, then what this means is that it's hard for the prover to come up with p1 star such that hash of P1 star, which is R1 in this figure, is equal to a root of the polynomial, that is a root of this specific polynomial, which is P1 star minus this second term. And similarly, hash of P2 star should not equal the root of the polynomial, that's P2 star minus respective second term, and so forth. Okay, so here's the overall structure for how we will proceed. I'm sorry, I don't know why that's happening. Yeah, so our goal is basically going to be to design a hash function that helps us avoid these bad challenges. And so to understand how this will happen, we will consider the setting where the prover breaks soundness. That means, suppose there's a prover that's able to prove a false statement to the verifier. We will try to say that the prover actually managed to use this hash function and find a bad challenge in this hash function. So like we discussed a few slides ago, if the prover does manage to provide an accepting proof for a false statement, then there must exist some step I where the non-interactive prover switched from proving a false claim to proving a true claim. And as we just discussed, this necessarily means that the value Ri is a bad challenge or is a root of the following polynomial. And ideally, we would like to show that such a prover can be used to contradict the correlation-intractability property for the ith hash function. So in order to do this, we must design a hash function that avoids this bad challenge Ri. And we will now make multiple attempts to define an appropriate hash function. So recall that we said that the work of Pikert and Sheehan and Canetti et al. Built a CI hash function for specific types of functions, namely for efficiently computable, sparse enough bad functions F. So what this means is that as the bad challenge, we care about ruling out functions that are efficiently, if we care about ruling out functions that are efficiently computable, then we can directly invoke their result. So what do I mean? So in our first attempt, we're just going to try to see if the hash functions that were built in previous work can be used as is. And the point is they can be used if the bad challenge function is efficiently computable. But as you can imagine, this turns out to not be the case. So again, even if you don't know the SumCheck protocol in detail or don't know why this is true, the important thing to remember is that the SumCheck protocol has this structure where in every round, there's just a few verifier challenges that will allow the prover to continue to cheat. And for most verifier challenges, the prover will have absolutely no way of cheating. And the verifier challenges that do allow the prover to cheat are what we call bad challenges. And we want to design a hash function that for which it's hard for the prover to come up with inputs such that hashing those inputs leads to bad challenges. Okay.
So just a question.
Yes.
So the polynomial whose root we should not hit is also somewhat implicitly defined, right? One half of it, the pi star, is sort of explicit in the message, but the other one is something which perhaps the prover can do with a lot of time, but the verifier will not know that polynomial.
Yes, that's exactly. So you've hit the nail on the head, and that's exactly the problem here. Indeed, the first term is explicit, the prover is providing pi star. The second term is p star evaluated on R1 to Ri minus 1, and then summed up over all possibilities of xi plus 1 up until xn. So summing up over all possibilities of xi plus 1 up until xn is clearly very inefficient. It's not something the verifier can do. The prover can do this, but the prover is trying to cheat. So it's not going to, like, you need to find a way for the prover to actually do this properly. So that's not what we're going to do. What we will do instead is like understand that what we want to rule out what we want to say is that the hash function is not going to hit a root of this specific polynomial. And this polynomial is not efficient to compute. And that's the exact problem. So previous work would have already solved this problem if this polynomial was in fact efficient to compute. And so that's what I'm trying to say on this slide, that previous work is inapplicable because the second term is extremely inefficient. And because it's so inefficient, that inefficiency is going to get transmitted also to the hash function. So If we naively attempted to compute the second polynomial, this would involve sums over 2 to the n points, and this is clearly not efficient. But if we somehow knew what these verifier challenges R1 to Ri minus 1 were going to be in advance, oops, I'm so sorry. I was trying to point and I accidentally stopped sharing. Yes, so if we somehow knew what these R1 to Ri minus 1 values were in advance, then we could hope to maybe compute this second polynomial in some pre-processing stage. So towards trying to solve this problem, like our first idea is to try to pre-process this polynomial. So what do I mean? Before the game begins, we will non-uniformly try to fix some type of advice string that already contains an evaluation of this polynomial. If we do that, it turns out that that's sort of efficient enough, not efficient enough, but this type of non-uniform argument is sufficient for cryptographic reductions to go through, as long as we assume that learning with errors is hard against non-uniform adversaries. So essentially, we'll consider a setting where an adversary gets some advice after an unbounded amount of pre-processing. But then given this advice, after getting this advice, the game begins. So randomness for our learning with errors samples comes only after the adversary has received this advice. And once the game begins, it's hard for the adversary to actually break our underlying assumption.
Just to understand, sorry, this thing about advice, etc., is just part of your proof, or it will be part of the protocol? I mean,
yes,
this is just for the argument.
Only a part of the proof. Yeah, this is just for the proof of security. Exactly.
Got it. Thank you.
The protocol is exactly what we saw before. Like you have the subject protocol. We'll set a specific hash function. What we're trying to do now is define this hash function. But once we have the hash function, the protocol is simply going to be compute your interactive message, hash it, get the verifier's randomness, and continue. So that's it. The protocol is going to be as simple as that. Yeah, all of this is to actually get a proof of security. And I'm just trying to illustrate the bottlenecks that existed. So the reason that this was not a solved problem was because this term was inefficient. And our first wrong idea, or first idea that doesn't quite work, is to say, well, what if we could pre-compute this second term in a non-uniform phase, if we somehow knew what the verifier challenges were going to be? Now, again, even if you don't follow all the details of the subject protocol, it is going to suffice to think from this point on about any general interactive protocol where one can define a bad challenge of the verifier. Basically, one can define challenges that allow the prover to cheat and are sparse, and such that for most challenges, the prover cannot cheat. And these bad challenges can be computed in two parts. One is an efficient part, which is basically the prover just gives you PI star. So this is clearly efficient. You can read it. And the next is an inefficient part that depends on the verifier's previous challenges. And we will think of trying to compute this in an offline phase that is inefficient before the protocol even begins. Okay, and another way of thinking about this is that the second term is like a trapdoor. It depends only on verifier messages R1 to Ri minus 1. And the first part is an efficient function of the prover's online messages. Now, more importantly, this trapdoor is not going to be efficiently computable online, but we're going to try to compute it offline. Now, there's an important challenge here. We don't know what R1 to Ri minus 1 are going to be. And in fact, the prover is going to be generating these values on the fly. So, okay, sorry, let me just add here that recall that the values R1 to Ri minus 1 in the interactive proof are actually the verifier's challenges. And in the non-interactive argument, we said that all that the prover is going to do is continuously hash the transcript so far and use those hash functions as its randomness values R1 to Ri minus 1. Okay. So what this means is, okay, sorry, let me just, what this means is that R1 to Ri minus 1 are being computed on the fly. And because these are being computed on the fly, what does it mean to pre-compute this? We don't even know what R1 to Ri-1 are going to be in the actual protocol. And so this was the main bottleneck again in prior work in terms of trying to compute this term. And what we say is we're just going to guess these values. So what we'll do is these values R1 to Ri-1, we don't know what they're going to be. So in this pre-computation offline phase, we'll just make a random guess. Now, and we can see that if we knew what R1 to Ri-1 were going to be, then in an offline or pre-processing phase, we could compute the second term inefficiently as a function of our guessed values. Okay. Now, this is, sorry. Yeah, if we guess these values, the problem is that we will succeed in guessing all of them correctly only with probability 1 over the field size raised to the I-1. So I'm sure that when I said we'll guess them, this must have raised some questions because guessing is clearly not going to give us what these, like guessing is clearly going to fail with high probability, and only with a very small probability will we actually succeed in guessing them correctly. So the problem is that the ith hash function is going to output a field element, and as such is going to have maximal security, that's 1 over size of field. So the probability with which we successfully guess is going to be much, much lower than the security offered by the hash function. And that's why this type of guesswork is going to fail, as I think may already be intuitively evident to you. Okay, so in other words, the problem is that the probability of guessing previous challenges is too low and is not sufficient to rely on and it is not sufficient to guess correctly in order to rely on the security of the ith hash function. So in our next attempt, we are going to choose R1 to Ri-1 carefully to derive a contradiction for the ith hash function. I'm sorry, I think this should say carefully, and I'm sorry, I think there's been some issue with the slides. So, so when we choose these, what we'll do is in our next attempt, we'll choose each of these randomnesses to be polynomially larger than the previous one. And I'm not going to go into the details of these parameters, but we'll just say that Ri has a polynomial dependence on the previous value, on the range of the previous randomness Ri-1 and so forth. And because we have the randomness growing in this way, one can actually use a clever setting of parameters so that at any point I in the protocol, all the previous randomnesses are relatively efficiently guessable compared to the security of the ith hash function. This means that we will be able to say that if a prover breaks soundness by going from a false claim to a true claim at some step I in the protocol, then by guessing all these previous values R1 to Ri-1, we will still be able to guess them with a large enough probability that we will be able to rely on the security of the ith hash function and say that any prover that breaks soundness will give us a direct contradiction to the correlation intractability of the hash function. So while this seems to work at first glance, actually we run into a problem pretty quickly. The problem is the following, that this constrains the number of times we can grow this randomness to something like log size of field. Again, there's a bunch of calculations that needs to happen here that I'm throwing under the rug. And let me just say that ideally we would like the number of times we can grow this randomness to be something like, I'm sorry, this should be log size of the field. So we don't want it to be as restrictive as what we get here. We want it to be log size of field. There should be only one log here. And we ran into this problem because we attempted to reduce the space of challenges of the verifier in the protocol itself. Like again, we said that the verifier's first challenge is chosen from a smaller field, from a smaller subfield. The second randomness is chosen from a slightly larger subfield, and so forth. Instead of doing this, the idea that works is the following. Instead of reducing the challenge space in the protocol itself, we're going to reduce the challenge space artificially only in the proof of security. So this means that in our protocol, all the verifier randomnesses R1 to Rn are chosen uniformly at random in the field. the size of all these randomness values is therefore going to be logarithmic in the size of the field. But in our proof, we are going to be able to flip a switch so that when the switch is flipped, R1 up unto Ri minus 1 are sampled from a much smaller space, such that sampling from this smaller space is actually indistinguishable from sampling something that's uniformly random. So again, the core idea is to introduce this type of switch so that in the proof of security, we are able to switch R1 to Ri. So let's say we are zooming in on the ith execution, and we know that the prover switched from proving a false claim to a true claim in exactly the ith step. When zooming in on this step, we're going to be able to artificially reduce the size of the space of R1 to Ri minus 1 in such a way that the adversary cannot tell the difference. So the adversary doesn't know if we sampled R1 from the entire space or from a secret hidden subspace within the whole space. And the same for all the randomnesses between R1 and Ri minus 1. And this will make it so that artificially we will increase our probability of guessing these values and therefore doing the pre-processing, while at the same time, all values from R1 to Rn are going to be from this larger space. And this helps us guess previous values while getting a contradiction for the ith step. So that's all I'm going to be able to say about this idea here, but I'm happy to answer any questions that you have about the specific idea. Okay, so what remains now is to find an appropriate hash function that enables us to flip a switch in this way. So can we basically design a correlation-intractable hash function where after we flip a switch, we have that R1 to Ri minus 1 are all sampled from a smaller space, and Ri to Rn are all sampled from a much larger space. So does there exist a hash function that can have this type of mode built in? And as it turns out, this type of mode was introduced in a different setting in a prior work on lossy trapdoor functions. So this was an influential work of Pikert and Waters, and they showed that one can build what is called a lossy trapdoor function, which is a keyed function that has two key generation modes. In an injective mode, so again, this is a hash function with two modes. In an injective mode, the output space is large, and in a lossy mode, the output space is small. So this is 2 to the lambda to the epsilon for some small epsilon. And to an adversary, these two modes appear indistinguishable. So this is a lot like sampling from a larger space or sampling from a small hidden space, and the adversary can't tell the difference between the two. And these two modes have the following properties. The first property is injectivity, which means that the injective mode outputs a trapdoor and allows you to invert the function. That means the function can be computed in the forward and reverse directions efficiently given this trapdoor. And the second property is key indistinguishability, which means that whether you're injective or whether you're lossy, these two modes are indistinguishable from each other. And Pikert and Waters 12 years ago built these types of functions under the learning with errors assumption. So inspired by these lossy trapdoor functions, what we do is we introduce this notion of a lossy correlation-intractable hash function. And now, as you recall, we needed correlation intractability to ensure that the prover cannot compute these bad challenges. And moreover, we are going to add this extra lossy property to it to allow for the type of cheating that we wanted. So I'm just going to quickly, the construction of this is not going to be very relevant again to what we do. It's fairly simple. We just build lossy CI hash functions under the sub-exponential LWE assumption by composing, I don't know why this is happening. By composing a correlation intractable hash function with a lossy trapdoor function. And I'm going to skip the details of how we build this and just move to the final protocol. So our final protocol is basically has a CRS that has a bunch of keys for a lossy correlation intractable hash function. And this hash function has this extra switch property that I talked about. And the rest of the protocol is basically the prover first computes the first polynomial, hashes it to get the verifier's randomness, then computes the second polynomial, hashes the transcript so far to get the verifier's next randomness, and so forth. And so basically the rest of this can be seen as applying the Fiat-Shamir transform to the subject protocol, but with a lossy correlation-intractable hash function that instead of giving a heuristic proof of security actually allows for a concrete proof of security based on the learning with errors assumption. So I'm going to skip these parts because I'm fairly over time already. But I was going to sketch the proof of soundness. Maybe if anyone has questions about this, I could instead address those. And I'm just going to display
I was trying to get a sense of where does the fact that you're working with a constant depth circuit show up?
Right, that's a good question. Yes, I never got to that. So so far I've been talking about the subject protocol. What we actually are able to do is generalize this technique to also compress other interactive proofs. And in particular, what we are able to compress is the GKR interactive proof. So this is a famous interactive proof by Goldwasser, Kalai, and Rothblum. And they build interactive proofs for bounded depth circuits. So it's inherited from that protocol, from that interactive protocol that we are compressing. Another way to think about it is that the number of rounds in that interactive protocol grows with the depth of the circuit. And so that's very roughly like if you think about n here, n is actually equal to the depth of the circuit in that specific protocol. And so, so that's why our protocol grows with the depth of the circuit. So I'm going to skip the proof of soundness. Hopefully you all already have an idea from pictures what this looks like. Like suppose a prover breaks soundness, then there's some step I at which the prover switched from a false claim to a true claim. Zoom in on that step, and now once we have zoomed in on that step, flip the switch so that the randomness for all previous steps comes from a small space and the randomness for all future steps comes from a large space. And now once you flip the switch, you can easily get a contradiction based on the properties of the hash function. So I'm not going to talk about the details of that, just going to wrap up. Okay. Yeah.
Can you go back to the previous slide?
Yes.
So here you require that n times lambda to the epsilon to be smaller than lambda to the delta.
Correct. Yes. 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 Those are the exact parameters. Yes. So I skipped over these things, but yeah, we will set these parameters carefully so that the CI property has parameter lambda to the delta, where delta is going to be much larger than n times lambda to the epsilon. Yeah. So we can go basically for n can be as large as lambda to the epsilon, for example. Okay. So in summary, we build these special types of hash functions from sub-exponential LWE, and we use them to get a non-interactive version of the subject protocol under standard cryptographic hardness assumptions. This was not known before. And since the subject protocol is so fundamental, using this non-interactive compression of the subject protocol, we are able to actually define a much larger class of interactive proofs that goes beyond subject, for which the Fiat-Shamir transform that I told you about can be provably instantiated from lossy correlation-intractable hash functions. So basically, we define a large class of interactive proofs that can be similarly compressed. And within this class lies this specific GKR protocol, which is basically a proof, which is an interactive proof for bounded depth delegation. And we compress this proof to get SNARGs for bounded depth circuits. And again, by relying on this work of Choudhuri et al., who showed that if you can compress the sum check, then you get PPAD hardness results. We say, well, you can compress the sum check from sub-exponential LWE, and therefore by invoking their beautiful techniques, we also get PPAD hardness from the same assumption. So now let me just end with some open problems. I think some more obvious open problems that we don't address are compressing other types of interactive protocols, including more general interactive proofs, proofs that may not follow this nice bad challenge paradigm where some part is efficient, the other part is inefficient, but can be efficiently computed in a pre-processing. So it can be computed in a pre-processing phase. So like we relied on the specific structures of some check, and all interactive proofs may not have this structure. So it's still open whether one can compress more general categories of interactive proofs. It's also unknown if more generally interactive arguments can be compressed. So again, all these techniques are very tailored to compressing proofs, which are sound against unbounded provers. And it's unclear whether we can compress interactive arguments. Another question of interest is to build these types of hash functions from other assumptions that are standard in cryptography, such as the decisional Diffie-Hellman assumption or the hardness of factoring. These are all classic cryptographic assumptions. And a consequence of building these hash functions from these assumptions would be, via our results, would be that we would directly get, for example, the hardness of PPAD from factoring or from the decisional Diffie-Hellman assumption, which would give us even more confidence in the hardness of the complexity class PPAD. And so that's, and another open problem is getting these things to work from polynomial hardness assumptions. So in particular, and this is something I swept under the rug in this talk, but to make these parameters work out, and because we're guessing things, we actually need to rely on the hardness of LWE against machines that run in more than polynomial time, in some amount of sub-exponential time. And what is more standard typically in cryptography is to try to assume that learning with errors is hard against polynomial time machines. So there's a gap there that would be nice to close. But yeah, that brings me to the end of my talk. And thank you so much once again for having me here, and very happy to answer any remaining questions. And sorry, I went over time.
So I have one quick question. So is it like so suppose you could construct like a succinct, I mean, these SNARGs for, let's say, constant depth circuits, or for even just for the sum check protocol. Does any such construction necessarily give you a correlation-intractable hash function or something? I mean, can you say that if there was a different construction, then embedded with inside it must be one of these primitives?
That's a really interesting question. I don't think we can say that. I think it's just the lack of other techniques to do this. So I think it's, yeah. I think it's really like the only way we know to attack these problems is via the Fiat-Shamir transform, at least in the specific setting that we care about, where there's a common reference string and a single message from the prover to the verifier, and we have publicly verified, and the argument is publicly verifiable, meaning anybody can check this argument. This is, as far as I know, the only approach to solve the problem, but that I think is very far from saying that any approach must embed inside it a lossy CI hash function. So yeah.
Okay. Any other question? All right. So, yeah. So,
okay. Thank you for hanging in there.
Thanks a lot for the talk. It was very